All right, folks, let's talk about Tier 3 indeterminate forms and the techniques required to evaluate limits using these Tier 3 forms. So here we are introduced to them. Tier 3 indeterminate forms are 0 to the 0. That's a weird one. It's not 0. It's not 1. It's, I don't know. It's a small number to a small power. Now, the next one is infinity to the 0. That is an indeterminate form as well. Infinity is not a real number, so you can't say anything to the 0 power is 1 because this isn't anything. So that's a weird one. 1 to the infinity is not necessarily 1. Remember that this isn't exactly 1. This is in the limit as we approach a certain value. So this 1 value, although we say 1 here, it could be a number a little bit less than 1, in which case raising it to a large number is going to make it dwindle down to 0. Whereas if it's a number that's a little bit bigger than 1, raising it to a large number is going to make it skyrocket. And the same is actually true here, just the reciprocal. So some key notes here. You cannot use L'Hopital's rule directly on this form. What you have to do is rewrite first as Tier 2, then again as Tier 1. So this is a two-step process. This typically will be an expression that involves a variable in both the base and the exponent. So something like an f of x raised to a g of x power. And the standard technique to deal with this is you're going to, maybe I should put that power in there. You're going to have the limit as x approaches a of f of x raised to some g of x power. And what you're going to do, let me erase this and fix these notes on the fly. Oops. You are going to use the fact that that is equivalent to the statement the limit as x approaches a of e to the natural log of f of x raised to the g of x. And what that'll allow you to do is that'll allow you to bring your coefficient down, or your power down, excuse me, as a coefficient. And typically that turns it into a Tier 2 indeterminate form. So this is usually Tier 2, 0 times infinity. Sometimes you'll get lucky and it'll jump straight to a Tier 1, but not always. And then you'll basically treat it as a Tier 2 problem. Okay, so the common indeterminate forms are above, but these are not indeterminate forms. Infinity raised to the infinity, that's a large number raised to a large power. That's just exceedingly large. 1 to the 0 is actually 1, and 0 to the first power is also 0. So watch out. Don't lose sight of the things that you already know. Let's take a look at an example. Here, if we let x approach infinity, what we get is 1 plus 0 to the infinity, or 1 to the infinity power. Now, again, this is not 1. In fact, I dare say that this is a number that's a little bit bigger than 1 for the most part. So we need to be careful. This is indeterminate, Tier 1, and requires further analysis. And that further analysis is f of x is equal to e to the natural log of f of x. So what we're going to do is we're going to rewrite this limit. This is the limit as x approaches infinity of e raised to the natural log of 1 plus 1 over x to the x power. And we're going to do two things at this point. The first thing is we're going to note that the exponential function is continuous, and so we can move our limit through the function. And this is equivalent to e raised to the power of the limit as x approaches infinity. The other thing that we're going to do is we're going to bring that exponent down as a coefficient. That's why we rewrote it this way, so that we could bring that power down and get our filthy little hands on it. So this is x times the natural log of 1 over 1 plus x. Reevaluating this, what we get is e to the infinity times the natural log of 1, which is e infinity times 0. And this is Tier 2. Indeterminate product. And it requires more analysis. So let's do that analysis. What we're going to do is we're going to deal with that indeterminate product by writing this not as a product, but as division by the reciprocal of one of those factors. Now, this becomes e to the 0 over 0, which is tier 1, indeterminate. And the further analysis we're going to use now is L'Hopital's rule, but we're only going to use it up here in the exponent. So this is e, I'm using L'Hopital's rule now, to the limit as x approaches infinity, and we have, let's see, the derivative of the numerator is going to be 1 over the inside times the derivative of the inside over the derivative of the denominator, which is negative 1 over x squared. And we'll get some cancellation here, and this will reduce and be e raised to the limit as x approaches infinity of 1 over 1 plus 1 over x, which is e to the 1 over 1 plus 0, which is e to the first, which is just e. And that's our result. That's the limit. E is the limit. Probably didn't expect that. Okay. Last example. Here we go. Let's get an ugly looking one. This is the limit as x approaches e from the right of the natural log of x raised to the 1 over x minus e power. Isn't that creative? And when we do this, we get the natural log of e raised to the 1 over 0 positive, because we're using a number bigger than e. And that's equal to 1 to the infinity. And so we have the same indeterminate form. This is tier 3. Indeterminate form. It requires further analysis, and we're going to use that same f of x, whatever our function is e to the natural log of f of x. Now this may be a little bit confusing because our function already has natural logs in it. So watch your step. Here we go. This is equal to the limit as x approaches e from the right of e to the natural log of the natural log of x raised to the 1 over x minus e power. And we're going to do two things here. The first thing I'm going to do is I'm going to run that limit up into the exponent of our function here. And the other thing I'm going to do is I'm going to bring down that power as a coefficient. So this becomes the natural log of the natural log of x over x minus e. And when I try to evaluate that limit, I'm going to get e to the, well, as e goes to, or as x goes to e from the right, I'm going to get the natural log of e, which is 1, the natural log of 1, which is 0, and I get 0 over 0 again. So this is indeterminate, tier 1, requires further analysis, but this one we can use L'Hopital's rule on. So let's do that. We're going to use L'Hopital's rule up in the exponent. Why do these e's look so atrocious? Let me fix those. E raised to the limit as x approaches e from the right. In the denominator, the derivative is just 1. In the numerator, the derivative is 1 over the inside times the derivative of the inside. And what we get here this time when we evaluate the limit is e raised to the 1 over the natural log of e times 1 over e all over 1. The natural log of e is 1, and this becomes e to the 1 over e. And that's our result. Let me fix that circle. And that is our result. Ooh, the limit exists. And that's going to do it. Attack that homework, folks, and I'll see you in office hours.